Alright, in this video we're going to be looking at improper integrals. This is from section 3.7. To contrast improper integrals with proper integrals, let's define a proper integral. So if f is continuous on a closed interval ab, then the integral from a to b f of x dx is the definite integral, or proper integral. Improper integrals will have infinite limits of integration or finitely many infinite discontinuities on the interval that we're going to be integrating. So let's go ahead and look at if f is continuous on the half open or half closed, it's both, closed at a off to infinity, then the integral from a to infinity of f of x dx is defined to be the limit as b goes to infinity of the integral from a to b f of x dx. We can also go to minus infinity. If f is continuous on the interval negative infinity to b, including b, then the integral from negative infinity to b of f of x dx is equal to the limit as a goes to negative infinity of the integral from a to b f of x dx. If f is continuous on the entire real number line, then the integral from negative infinity to infinity of f of x dx is equal to the limit as b goes to negative infinity of the integral from b to 0 f of x dx plus the limit as a goes to infinity of the integral from 0 to a of f of x dx. Or you could use really any number c in place of 0, but 0 is a nice easy number to use. For 1 and 2, that's the half open, half closed a to infinity or negative infinity to b. If those limits exist, we say that the integral is convergent. For 3, if both the limits exist, then we say the integral is convergent. If any of the limits do not exist, then we say that the integral is divergent. Okay, so let's try some out. Look at example 1. And we're going to find the integral from 1 to infinity of dx over x to the fourth. And so this means the limit as b goes to infinity of the integral from 1 to b. Let's go ahead and rewrite the 1 over x to the fourth as x to the negative 4 dx. So it's going to be the limit as b goes to infinity, and we'll go ahead and integrate. So we'll add 1 to the exponent, divide by the exponent, and we're going to evaluate from 1 to b. So this is going to be the limit as b goes to infinity of negative 1/3, and then we're going to have 1 over b cubed minus 1 over 1 cubed. So we're just going to go ahead and evaluate, and then we're going to take the limit. So this is going to be negative 1/3. Okay, as b goes to infinity, 1 over b cubed is going to go to 0. And so this limit will become negative 1/3 times the quantity 0 minus 1, or 1/3. And this could be understood as the infinite area. Well, it's not an infinite area, but if we were to take this function and go off indefinitely, the area would converge to 1/3. So that'd be the area from 1 to infinity. So we'd be looking at this area right in here under the curve bounded by the x-axis. All right, so generically this is a p integral. Okay, so let's say that our p is greater than 1. So for example, 4 is greater than 1, so we have a p integral where p is 4. So we're going to look at the generically p is greater than 1. Then the integral from 1 to infinity of dx over x to the p is equal to the limit as b goes to infinity of the integral from 1 to b of x to the negative p dx. So we're going to go ahead and apply the power rule, and that's going to be the limit as b goes to infinity of x to the 1 minus p. So remember, you add 1 to the exponent, divide by the exponent. I'm going to evaluate from 1 to b. Okay, so p is greater than 1. So then 1 minus p, so if we take subtract p from the inequality here, we're going to have 0 is greater than 1 minus p, or 1 minus p is negative. Think of negative 3 in the previous problem there, okay? All right, so let's go ahead and work this out. So limit as b goes to infinity, we're going to factor out 1 over 1 minus p. Okay, and then we're going to go ahead and move the x to the 1 minus p, which is a negative exponent, to the denominator, which would be x to the p minus 1. We'll go ahead and evaluate it also. Minus 1 over 1 to the p minus 1. And p minus 1 is going to be greater than 0. All right, so when we take the limit, this is going to be 1 over 1 minus p. 1 over b to the p minus 1. P minus 1 is positive, so that's going to go to infinity in the denominator, so we'll have 1 divided by a large number, so that's going to be 0, and then minus 1, and so that's going to be 1 over p minus 1, and so this converges. Now if you look at the previous problem, the exponent was 4, and so that converged to 1 over, your p was 4 minus 1, or 1/3. So we see that that works out in the previous example, so now we have it generically. So both integrals converge because we got a finite value. Okay, all right, so we say both integrals converge. We're going to look at p equals 1 and then p is less than 1, and that'll cover all our bases for p integrals. So if p is equal to 1, then it's just 1 over x to the first power, which is dx. Okay, so rewrite limit as b goes to infinity of the integral 1 to b, 1 over x dx, which is going to be the limit as b goes to infinity, natural log of the absolute value of x, evaluated from 1 to b, which is equal to the limit as b goes to infinity of the natural log of b minus the natural log of 1. Okay, now as b goes to infinity, the natural log of b is going to go to infinity as well. Natural log of 1 is 0, so this limit is infinity. Okay, and this can be interpreted as the area under the curve of the natural log of x, and so this area here is going to be infinite. And we'd say that integral diverges. So for our p integrals, what we have right now, so integral from 1 to infinity of 1 over x to the p dx, that is going to converge to 1 over p minus 1 if the p is greater than 1, and it's going to diverge if p is is equal to 1. And then we're going to look at the case where p is less than 1. So to motivate that, let's take a nice concrete number like 1/3, which is less than 1. So the integral from 1 to infinity of 1 over x to the 1/3 dx is equal to the limit as b goes to infinity of the integral from 1 to b of x to the negative 1/3 dx, which is equal to the limit as b goes to infinity, x to the 2/3 divided by 2/3 evaluated from 1 to b. So that's going to be the limit as b goes to infinity. Flip the 2/3 over to make it 3/2. B to the 2/3 minus 1 to the 2/3. Okay, and as b goes to infinity, so does b to the 2/3. That's the cube root and then squared, so that's certainly going to go to infinity. And so this would be a divergent integral. And so we're going to use that as kind of motivation to kind of follow along when p is less than 1. So if p is less than 1, the p integral from 1 to infinity of 1 over p dx is going to be the limit as b goes to infinity of the integral from 1 to b, x to the negative p dx was equal to the limit as b goes to infinity. And we're going to add 1 to our exponent and divide by our exponent, evaluated from 1 to b. Okay, so p is less than 1, so if we subtract p from both sides, 0 is less than 1 minus p, or in other words, 1 minus p is positive, so we're not going to move it, it's going to stay in the numerator. So this is going to be equal to the limit as b goes to infinity of 1 over 1 minus p, b to the 1 minus p minus 1 to the 1 minus p. All right, now b to the 1 minus p, that's a lot like b to the 2/3. And so what's going to happen to that is as b goes to infinity, the b to the 1 minus p is also going to go to infinity, and so that's going to diverge. Okay, so the integral from 1 to infinity of 1 over x to the p dx is going to diverge for p less than 1. Okay, and so we'll summarize this on the last slide. We might do one more slide actually. So I'll p to integral. The integral from 1 to infinity of 1 over x to the p dx is going to converge to 1 over 1 minus p, 1 over p minus 1 if p is greater than 1, and it's going to diverge if p is less than or equal to 1. Okay, so I have the three p integrals, the concrete ones that we graphed. Now in red, which I'll highlight in kind of a weird green color, notice that it gets real close to zero real quick there. And so that area is convergent. You're not going to accumulate very much in the tail there. And I think we said that that area was 1/3. Okay, now 1 over x is this graph here. And it does not crash down to zero quick enough. And so the area there is going to be infinite if we continue on this process. And likewise, the 1 over x, the 1/3, is going to be this one here, and we are accumulating way too much area there, so that's going to be an infinite area. And so we say that's divergent. Okay. Now the p integrals will come into play in the next chapter, I think section 5.3, when we look at the integral test. We are going to be comparing something called a p-series with a p-integral. And it so happens with the integral test that a p-series and a p-integral will end up doing the same thing. They'll either both diverge or they will both converge. And so I think we'll be looking at that next week. So stay tuned for the next video on the improper integrals. We'll see you then.